This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Hello and welcome to our exploration of recent scientific research into one of Earth's most intriguing and impactful events, the Late Devonian Mass Extinction. In this video, we'll dive deep into the fascinating world of paleontology, geology, and ecology to uncover the latest findings and theories surrounding this pivotal moment in our planet's history. The Late Devonian Extinction, which occurred approximately 372 to 359 million years ago, was a time of immense upheaval and change. It saw the demise of countless species, the restructuring of ecosystems, and the paving of the way for the rise of new life forms that would shape the future of Earth. Understanding the causes, consequences, and context of this extinction event is crucial not only for scientists but for anyone with a curiosity about the natural world and our place within it. In the following segments, we'll explore a range of themes and topics related to the Late Devonian Extinction. From the potential triggers and mechanisms behind the event to its impact on marine life, from the role of global cooling and ocean anoxia to the influence of plants and vegetation, we'll examine the many facets of this complex and multifaceted phenomenon. We'll also delve into questions surrounding the timing and duration of the extinction pulses, the event's long-term effects on biodiversity, and how it compares to other mass extinctions throughout Earth's history. As we embark on this journey through the Late Devonian, it's important to remember that our understanding of this distant past is constantly evolving. Each new discovery, each fresh perspective, adds another piece to the puzzle, helping us to refine our knowledge and appreciate the incredible complexity and resilience of life on Earth. So let's approach this topic with open minds, ready to learn, to question, and to marvel at the insights that science can offer. Whether you're a student, a researcher, or simply someone with a passion for understanding our world, we hope that this video will inform, engage, and inspire you. So sit back, relax, and join us as we unravel the mysteries of the Late Devonian Extinction. Topic 1. Causes of the Late Devonian Extinction. The Late Devonian Extinction, one of the 5 largest mass extinctions in Earth's history, has been the subject of intense scientific investigation for decades. Researchers have proposed a wide range of potential causes, each supported by various lines of evidence. One prominent theory points to the rapid expansion of land plants during the Devonian period. As plants spread across continents, their roots began breaking down rock at an unprecedented scale, altering global geochemical cycles. This increased weathering may have led to a drawdown of atmospheric CO2, triggering global cooling and lowering sea levels. Additionally, the influx of nutrients from land into the oceans could have fueled algal blooms, depleting oxygen levels and creating inhospitable conditions for marine life. Another possible driver of the extinction is volcanic activity. The Late Devonian saw the eruption of large igneous provinces, such as the Valui traps in Siberia. These massive eruptions could have released significant amounts of greenhouse gases, altering the climate and ocean chemistry. The resulting acidification and anoxia may have been particularly detrimental to reef ecosystems and other marine organisms. Some scientists have also proposed that asteroid impacts played a role, with evidence of crater structures and shock quartz dating to the Late Devonian. However, the link between these impacts and the extinction remains debated. It's likely that a combination of factors, rather than a single cause, was responsible for the Late Devonian extinction. The complex interplay of climate change, ocean chemistry, volcanic activity, and ecological shifts created a perfect storm that pushed many species to the brink. As research continues, scientists are working to untangle these various threads and build a more comprehensive understanding of this pivotal event in Earth's history. Topic 2. Impact on marine life. The Late Devonian extinction had a profound impact on marine life, resulting in the loss of an estimated 70 to 80% of species. Reef ecosystems were hit particularly hard, with the collapse of the extensive Metazoan reefs that had dominated the Devonian seas. Stromatoporoid sponges and rugose and tabulate corals, the primary reef builders of the time, suffered major losses, and reefs would not recover their former glory until the Mesozoic era. Other groups that experienced significant declines included trilobites, brachiopods, conodonts, and ammonoids. Interestingly, the extinction patterns were not uniform across all marine habitats. Shallow water, tropical ecosystems bore the brunt of the losses, while deep water and high-latitude communities were less severely affected. This disparity suggests that factors like changes in sea level, ocean temperature, and oxygenation played a key role in determining which species survived and which succumbed. The aftermath of the extinction saw a major restructuring of marine ecosystems. Groups that had previously been minor components of the fauna, such as sharks, bony fishes, and crinoids, underwent substantial radiations in the wake of the crisis. These winners of the extinction filled the ecological niches left vacant by the demise of the dominant Devonian groups, setting the stage for the marine communities of the Carboniferous and beyond. The Late Devonian extinction thus stands as a stark reminder of the power of global change to reshape the course of evolution and the composition of Earth's biosphere. Topic 3. Anoxic ocean conditions. One of the key factors implicated in the Late Devonian extinction is the spread of anoxic conditions in the world's oceans. Anoxia refers to the absence or severe depletion of dissolved oxygen in water, creating an environment inhospitable to most marine life. The Late Devonian saw several episodes of widespread anoxia, most notably the Kellwasser events near the Frasnian-Famennian boundary. The development of anoxia during this time may have been linked to a combination of factors. The rise of land plants and increased weathering could have flushed nutrients into the oceans, fueling algal blooms that consumed oxygen as they decayed. Warming temperatures, driven by volcanic activity or other factors, may have reduced the solubility of oxygen in seawater and slowed ocean circulation, exacerbating the problem. The result was the spread of dead zones, where most aerobic life could not survive. The impact of anoxia on Late Devonian marine life was severe. Benthic organisms, living on or in the seafloor, were particularly hard hit, as they require oxygenated conditions to thrive. Reef ecosystems, which were built by sessile, oxygen-dependent organisms like corals and sponges, collapsed in the face of spreading anoxia. Pelagic species, living in the water column, may have been somewhat buffered by their ability to move to more oxygenated areas, but they too suffered losses as food webs were disrupted. The anoxic events of the Late Devonian left their mark in the geological record in the form of widespread black shale deposits. These organic-rich sediments, laid down under oxygen-poor conditions, provide a window into the environmental upheaval of the time. As scientists continue to study these deposits and the fossil record of the Late Devonian, they are piecing together a clearer picture of the role that anoxia played in this major extinction event. Topic 4. Global cooling and glaciation. The Late Devonian was a time of significant climate change, with evidence pointing to a period of global cooling and glaciation. This shift in climate is thought to have played a key role in the extinction events of the time, particularly the Hangenberg event at the Devonian Carboniferous boundary. Several factors may have contributed to the cooling trend. The rise of land plants and the weathering of silicate rocks could have drawn down atmospheric CO2, a potent greenhouse gas. Volcanic activity, while potentially warming in the short term, may have also had a cooling effect in the long run by releasing sulfur aerosols that reflect sunlight. Orbital cycles, such as changes in the Earth's tilt and eccentricity, could have also influenced climate patterns. The evidence for Late Devonian glaciation comes from various sources. Glacial deposits, including tillites and dropstones, have been found in sediments dating to this time, particularly in regions that were located over the South Pole, such as South America and Africa. Changes in sea level, inferred from shifts in sedimentary patterns, suggest the growth and retreat of ice sheets. Oxygen isotope data from fossil shells also indicate a cooling trend. The impact of global cooling on marine life would have been significant. Lowered sea levels, caused by the formation of ice sheets, would have reduced the area of shallow marine habitats that were home to the majority of Devonian species. Cooler temperatures may have also directly stressed organisms adapted to warmer conditions, particularly in the tropics. Changes in ocean circulation patterns and nutrient cycling could have further disrupted marine ecosystems. While the extent and precise timing of Late Devonian glaciation remain topics of ongoing research, it is clear that climate change played a significant role in the extinction events of the time. The study of this ancient period of cooling provides valuable insights into the complex interplay of factors that can lead to major environmental shifts and biotic crises. Topic 5. Role of plants and vegetation. The Devonian period saw a major transformation of Earth's land surfaces, as plants evolved from small, simple forms to large, complex trees and forests. This greening of the continents had far-reaching effects on global environments and is thought to have played a significant role in the late Devonian extinction events. The rise of land plants began in the early Devonian, with the appearance of small, non-vascular species. By the Middle Devonian, vascular plants had evolved, allowing for the transport of water and nutrients and enabling plants to grow taller and colonize drier areas. The Late Devonian saw the emergence of the first forests, with tree-like forms such as Archaeopteris reaching heights of up to 30 meters. The spread of plants had major impacts on Earth's carbon and water cycles. Photosynthesis drew down atmospheric CO2, potentially contributing to global cooling. The decay of plant matter also released nutrients into rivers and oceans, which could have fueled algal blooms and anoxia. The development of deep roots accelerated weathering, altering soil chemistry and the flow of nutrients and minerals. The rise of plants may have also had direct effects on marine life. The influx of nutrients from land could have initially boosted marine productivity, but the resulting eutrophication and anoxia would have been detrimental in the long run. Changes in atmospheric CO2 and climate could have further stressed marine ecosystems. Some scientists have also suggested that the evolution of plant defenses, such as lignin and tough spores, may have disrupted marine food webs by making plant matter less digestible to herbivores. While the precise mechanisms by which plants influenced the late Devonian extinctions remain debated, it is clear that the greening of the continents was a major factor in the environmental and ecological shifts of the time. The study of this ancient plant radiation provides valuable insights into the complex feedbacks between life and the Earth system, and the potential for biological evolution to drive global change. Topic 6. Extraterrestrial impacts. One hypothesis that has been proposed to explain the late Devonian extinctions is the impact of extraterrestrial objects, such as asteroids or comets. The idea that impacts from space could cause mass extinctions gained prominence after the discovery of the Chicxulub crater and its link to the end Cretaceous extinction that wiped out the dinosaurs. In the case of the late Devonian, several lines of evidence have been put forward to support the impact hypothesis. One is the presence of impact craters that date to this time period. The Siljan crater in Sweden, for example, is a 52 kilometers wide structure that formed around 377 million years ago, close to the Frasnian-Famennian boundary. Other potential late Devonian impact sites include the Woodley crater in Australia and the Charlevoix crater in Canada. Another line of evidence comes from the presence of impact-related materials in late Devonian sediments. Microspherules, which are small, rounded particles formed by the condensation of vaporized rock during an impact, have been found in several locations, including Belgium and China. Elevated levels of iridium, an element that is rare in Earth's crust but more common in asteroids, have also been reported from some late Devonian sites. However, the impact hypothesis for the late Devonian extinctions remains controversial. Some scientists argue that the evidence for impacts is not as clear-cut as in the case of the end Cretaceous event, and that other factors, such as climate change and ocean anoxia, are more likely to have been the main drivers of the extinctions. Others point out that the late Devonian was a time of multiple extinctions spread over several million years, which is difficult to explain by a single impact event. Despite these debates, the study of potential impact events in the late Devonian remains an active area of research. The discovery of new impact sites or impact-related materials could shed further light on the role that extraterrestrial factors may have played in this tumultuous period of Earth's history. At the same time, the late Devonian serves as a reminder that mass extinctions are often the result of complex, interacting factors rather than a single cause. Topic 7. Timing and duration of extinction pulses. One of the key challenges in understanding the late Devonian extinctions is pinning down their precise timing and duration. Unlike some other mass extinctions, which appear to have been relatively sudden events, the Late Devonian saw a series of extinction pulses spread over several million years. The two most prominent extinction events are the Kellwasser event at the Frasnian-Famennian boundary, around 372 million years ago, and the Hagenberg event at the Devonian Carboniferous boundary, around 359 million years ago. However, there is evidence for other, smaller-scale extinctions throughout the Late Devonian, such as the Taganic event in the early Frasnian. The duration of these individual extinction pulses is also a matter of ongoing research. Some studies suggest that the Kellwasser event, for example, may have lasted for as little as 100,000 years, while others propose a duration of up to 2 million years. The Hagenberg event appears to have been somewhat shorter, with estimates ranging from a few 100,000 years to around 1 million years. One way that scientists have attempted to constrain the timing and duration of these events is through the study of magnetic reversals preserved in Late Devonian rocks. The Earth's magnetic field has flipped polarity many times throughout its history, and these reversals are recorded in the magnetic minerals of sedimentary and volcanic rocks. By matching the pattern of reversals in Late Devonian rocks to the global geomagnetic polarity timescale, researchers have been able to develop a more detailed chronology of the extinctions. Another approach has been the study of orbital cyclicity in Late Devonian sediments. The Earth's orbit and rotation are influenced by regular cycles in its tilt, eccentricity, and precession, which can affect climate and sedimentation patterns. By identifying these cyclical patterns in Late Devonian rocks, scientists have been able to develop high-resolution timescales and correlate events across different locations. Despite these advances, the precise timing and duration of the Late Devonian extinctions remain topics of ongoing research. The complex interplay of environmental factors, the limitations of the fossil record, and the challenges of precisely dating ancient events all contribute to the uncertainties. As new data and techniques emerge, our understanding of the tempo and mode of these extinctions continues to evolve. Topic 8. Long-term effects on biodiversity. The Late Devonian extinctions had profound and long-lasting effects on Earth's biodiversity. Beyond the immediate loss of species during the extinction events themselves, the aftermath saw major changes in the composition and structure of ecological communities that would shape the course of evolution for millions of years to come. One of the most striking effects was the decimation of the Great Devonian reef ecosystems. The stromatoporoid sponges and rugose and tabulate corals that had built these reefs were among the hardest hit by the extinctions, and reef ecosystems would not recover their former extent and diversity until the Mesozoic era, over 100 million years later. In the aftermath of the extinctions, reefs were much smaller and less diverse, dominated by microbes and algae rather than the complex metazoan communities of the Devonian. The extinctions also had major impacts on other marine groups. Trilobites, which had been a dominant part of marine ecosystems since the Cambrian, were greatly reduced in diversity and would never regain their former ecological importance. Brachiopods, crinoids, and ammonoids also suffered major losses, although some lineages would eventually recover and diversify in the Carboniferous and Permian. On land, the rise of vascular plants continued apace, but the extinctions may have impacted the early evolution of terrestrial vertebrates. The Late Devonian saw the appearance of the first tetrapods, the four-limbed vertebrates that would eventually give rise to amphibians, reptiles, and mammals. However, the precise relationships between the extinctions and the early evolution of tetrapods remain unclear, with some studies suggesting that the extinctions may have temporarily slowed their diversification. In the long run, the Late Devonian extinctions paved the way for a major restructuring of marine and terrestrial ecosystems. Groups that had been relatively minor components of Devonian communities, such as sharks, ray-finned fishes, and seed plants, underwent major radiations in the aftermath of the extinctions, taking advantage of the ecological opportunities created by the loss of previously dominant groups. The Late Devonian extinctions also had important implications for the overall trajectory of Earth's biodiversity. Some scientists have argued that the extinctions reset the evolutionary clock, wiping out many specialized and endemic lineages and creating opportunities for new groups to radiate and diversify. Others have suggested that the extinctions accelerated the trend towards increasing ecological complexity and diversity that had begun in the Cambrian. In many ways, the late Devonian extinctions can be seen as a turning point in the history of life on Earth. They marked the end of the age of fishes that had characterized the Devonian and set the stage for the rise of the tetrapods and the colonization of the land. They also demonstrated the vulnerability of even well-established and diverse ecosystems to rapid environmental change, a lesson that resonates strongly in our own time of global climate change and biodiversity loss. As we continue to study the late Devonian extinctions and their aftermath, we gain not only a deeper understanding of this pivotal moment in Earth's history, but also insights into the complex and often unpredictable interplay between life and the environment that has shaped our world for billions of years. Topic 9. Comparison to other mass extinctions. The late Devonian extinction is often considered one of the Big Five mass extinctions in Earth's history, alongside the End-Ordovician, Late Permian, End-Triassic, and End-Cretaceous events. However, it differs from these other mass extinctions in several key ways. One notable difference is the duration and pattern of the extinctions. While events like the End-Permian and End-Cretaceous extinctions appear to have been relatively rapid, with the bulk of species losses occurring over a few 100,000 years or less, the late Devonian extinctions were more prolonged and episodic, with multiple pulses of extinction spread over several million years. The magnitude of species loss also appears to have been somewhat lower in the late Devonian compared to some other mass extinctions. While estimates vary, most studies suggest that around 70 to 80% of species were lost in the late Devonian, compared to over 90% in the End-Permian extinction, for example. However, this still represents a major blow to global biodiversity. The causes of the late Devonian extinctions also appear to have been somewhat different from other mass extinctions. While impact events have been implicated in the End-Cretaceous and possibly other extinctions, the evidence for impacts in the late Devonian is less clear-cut. Instead, a complex interplay of factors including climate change, ocean anoxia, and the spread of land plants appears to have been the main driver. Despite these differences, the late Devonian extinctions share some common features with other mass extinctions. One is the differential impact on different groups of organisms. As in other extinctions, some lineages were hit much harder than others in the late Devonian, with reef builders, trilobites, and some groups of fish suffering particularly high losses. Another common feature is the role of environmental stressors, such as changes in temperature, sea level, and ocean chemistry, in driving the extinctions. Comparing the late Devonian extinctions to other mass extinctions can help us to better understand the general patterns and processes of these major biotic crises. It can also provide insights into the resilience and recovery of ecosystems in the aftermath of such events. For example, the slow recovery of reef ecosystems after the late Devonian extinctions may hold lessons for the fate of modern coral reefs in the face of climate change and other stressors. At the same time, the unique features of the late Devonian extinctions serve as a reminder of the complexity and contingency of these events. Each mass extinction has its own particular causes, patterns, and consequences, shaped by the specific environmental and evolutionary context in which it occurred. By studying these events in all their diversity, we can gain a richer understanding of the history of life on Earth and the forces that have shaped its course. As we've seen, the late Devonian extinctions were a time of major upheaval and change in the history of life on Earth. Over the course of several million years, a complex interplay of environmental factors, including climate change, ocean anoxia, and the spread of land plants, led to the loss of an estimated 70 to 80% of species, particularly in the marine realm. The impacts of these extinctions were profound and far-reaching. The once dominant reef ecosystems of the Devonian seas were decimated, not to recover for over 100 million years. Trilobites, brachiopods, and ammonoids suffered major losses, while groups like sharks and ray-finned fishes underwent significant radiations in the aftermath. On land, the rise of vascular plants continued, setting the stage for the eventual colonization of terrestrial environments by tetrapods. The late Devonian extinctions also offer important insights into the general patterns and processes of mass extinctions. They highlight the vulnerability of even well-established ecosystems to rapid environmental change, and the differential impact of extinctions on different groups of organisms. They also demonstrate the complex and often unpredictable interplay of factors that can lead to biotic crises, from changes in climate and ocean chemistry to the evolution of new life forms. In many ways, the lessons of the late Devonian extinctions resonate strongly with our own time. As we face the challenges of global climate change, ocean acidification, and widespread habitat loss, the fate of the Devonian reefs and the slow recovery of marine ecosystems serve as a stark warning of the potential consequences of unchecked environmental degradation. At the same time, the story of the late Devonian extinctions is also one of resilience and recovery. Despite the magnitude of the losses, life on Earth rebounded, with new groups diversifying to fill the ecological niches left vacant by the extinctions. This resilience is a testament to the adaptability and tenacity of life in the face of even the most severe challenges. As we continue to study the late Devonian extinctions and other major biotic crises in Earth's history, we gain not only a deeper understanding of the past, but also valuable perspectives on the present and future. By understanding the forces that have shaped the diversity of life on Earth over billions of years, we can make more informed choices about how to protect and sustain that diversity in the face of the challenges to come. As we conclude this exploration of the late Devonian extinctions, I want to thank you for joining me on this journey through one of the most fascinating and consequential periods in the history of life on Earth. I hope that you've come away with a deeper appreciation for the complexity and fragility of our planet's ecosystems, and the power of scientific inquiry to unlock the secrets of the past. If you've enjoyed this video and would like to learn more about mass extinctions and the history of life on Earth, I encourage you to check out some of the resources in the description below. And if you have any questions or comments, please feel free to leave them below. I'm always excited to engage with curious minds and explore these topics further. Once again, thank you for watching, and I look forward to joining you on future adventures through the wonders of science and the natural world.